Welcome to the Deep Dive, the show where we slice through complex research and deliver the insights you need to stay not just informed, but genuinely fascinated by the hidden world of technology around us. Today, we're plunging into a topic that might make you rethink how secure your digital life truly is. We're talking about invisible threats lurking beneath the surface of our most advanced security and, well, a revolutionary new defense that's fighting back with intelligence. Okay, let's unpack this. Cryptography, by its very nature, it's supposed to be uncrackable, isn't it? We pour immense trust into these intricate mathematical locks algorithms like AES 256, believing they safeguard our most sensitive data. We're talking secrets so well protected that trying to guess the key would literally take longer than the age of the universe. But what if the very act of a device doing its job, the subtle way it operates, subtly gives away those secrets?
What's truly captivating and frankly a bit unsettling is precisely that point. We're not discussing a software bug, coding error, or some vulnerability that allows someone to hack into your system through a network. Instead, side-channel attacks, or SCAs, exploit the subtle physical characteristics of a device as it processes data. Imagine something as fundamental as the electrical current a chip draws, or the faint electromagnetic radiation it emits, maybe even the precise time it takes for an operation to complete. These physical manifestations, they can be monitored and correlated to reveal secret keys, turning a theoretically impenetrable algorithm into a practical vulnerability right there at the hardware level.
And here's where it gets really significant for you, our listener. The shocking reality for something like AES 256, that's a cryptographic standard that's foundational to so much of our digital world, underpinning everything from banking transactions to secure communications, is its deep susceptibility. Once considered nearly impregnable, boasting a mind-boggling 2 to the power of 256 possible keys, SCAs can dramatically reduce its effective attack complexity. We're talking about dropping it to a staggering 2 to the power of 13. To put that into perspective, that's like going from needing to search every single grain of sand on every beach in the world to just a handful of buckets. That's how dramatically these physical attacks reduce the effort required. And get this. Attackers have been observed intercepting these keys from a distance using nothing more than a low-cost electromagnetic probe. It's a real-world danger that makes you think twice about how secure your smart devices, your personal data, even your car's keyless entry truly are.
It absolutely spotlights the urgent, ongoing need for fundamental innovation in hardware security. And that brings us to our mission today. We're taking a deep dive into Stellar, a truly groundbreaking new defense mechanism. This isn't just about building a stronger shield against these silent saboteurs, as you aptly call them. What makes Stellar truly revolutionary is its ingenious ability to not only fortify cryptographic systems, but also to detect when its own defenses are being targeted or probed.
That's the core of it. We're diving into the bleeding edge of hardware security, where the centuries-old cat-and-mouse game between attacker and defender gets incredibly sophisticated, moving from the realm of pure mathematics into the very physics of silicon. This isn't just about constructing a wall, it's about building a wall that screams when someone tries to dig under it. For you, the listener, this means understanding the hidden layers of security, protecting your smart devices, your financial transactions, your secure communications, and really the entire digital world we navigate daily. It's a deep dive into how engineers are fortifying the digital frontier against these truly stealthy physical attacks. So let's start by shining a brighter light on these invisible threats. We've talked about side-channel attacks, SCAs, and broad strokes. But what exactly are these leakage channels, and how do they manifest in the physical world, revealing secrets without any software breach?
The elegance, or perhaps the terror, of SCAs lies in their subtlety. They exploit the fundamental physics of how any electronic chip operates, transforming data processing into a physical signal that can be observed. The most common manifestations of these data-dependent physical leaks include variations in power consumption, faint electromagnetic radiation, precise timing differences in operations, and patterns in how data is accessed from memory caches. Let's explore each of these a bit.
Okay, starting with power consumption. That seems almost intuitive once you consider it. It's like a machine breathing, right? And its breath changes based on what it's doing.
Precisely. Yeah, good analogy. Every time a transistor switches state inside a chip, which happens billions of times a second when processing data, it draws a minuscule amount of electricity. This power consumption isn't constant. It varies, often minutely but measurably, based on the specific data being processed and the operations being performed. Imagine a light switch. Flipping it on takes a slightly different amount of energy than flipping it off. Or maybe the energy draw is different if the circuit connected to it is already active. A skilled attacker with specialized equipment, can monitor these minute fluctuations in current and voltage on the power lines of a chip, discerning patterns correlated with the secret key.
And then there's electromagnetic, or EM, radiation. That genuinely sounds like something out of a spy thriller, picking up signals from thin air.
It can certainly feel that way. Any electrical activity generates faint electromagnetic waves. These are the same types of waves that carry radio signals, but on a much smaller, localized scale and often at very specific low-power frequencies. A chip processing data creates these faint EM emanations, and just like power consumption, these emissions vary depending on the data being handled and the internal operations. Specialized probes, often called H probes, can pick up these distinct signals from a surprisingly close or even sometimes a short distance without ever physically touching the device. It's akin to listening for the specific hum a safe makes as its tumblers click, rather than trying to pick the lock directly.
And timing, we're talking about differences measured in milliseconds, microseconds, even finer granularities here, right?
All right. Indeed, often down to nanoseconds. The exact time it takes for certain operations to complete can inadvertently reveal information. For example, if an encryption algorithm takes slightly longer to process specific bits of data, or if a particular operation is skipped or altered based on the value of a secret key bit, that minuscule timing difference can be precisely measured and exploited. It's like noting how long it takes a secure door to unlock. A slightly longer or shorter whir of the mechanism might tell you something about the code being entered.
And finally, cache access. For those unfamiliar, a cache is like a super fast small memory right next to the processor, designed to store frequently used data for quick retrieval.
Exactly, yeah. When a cryptographic algorithm accesses data, it often does so in patterns that are dependent on the secret key. If an attacker can monitor whether data is retrieved from the lightning-fast cache or the comparatively slower main memory, those access patterns can reveal details about the computations and, by extension, hint at the secret key. It's about inferring internal operations by observing external side effects, an invisible dance between processor and memory that can betray secrets.
So how do attackers actually exploit all this subtle leakage? They're not just staring at an oscilloscope screen and magically seeing the key pop out, are they? There must be some, sophisticated analysis involved.
No, it's far more intricate. But crucially, it often doesn't require intimate knowledge of the chip's internal circuit design. This is a key point in its effectiveness. Attackers employ sophisticated statistical models. They monitor these physical signatures, the power traces, the EM emissions, and correlate them against statistical models based on secret key guesses. They don't need to know precisely what every circuit element is doing. They just need to guess what an intermediate value inside the chip should look like at a certain point if a specific key byte were correct.
Right, okay. And this is where concepts like Hamming weight and Hamming distance come into play, providing a way to quantify these guesses, isn't it?
Yes, precisely. Simply put, Hamming weight, HW, is the number of 1 bits in a binary number, and Hamming distance, HD, is the number of bits that differ between 2 binary numbers. The crucial point here is that these models allow attackers to estimate switching activity inside the chip. The more bits that flip from 0 to 1 or 1 to 0, which equates to a higher HW or HD, the more power is generally consumed, or the stronger the EM signature becomes. It gives them a measurable physical proxy for the data being processed. So an attacker will guess a portion of the secret key, calculate the expected HW or HD for a particular internal operation, and then compare that expected signature to the actual measured physical signature. A correct key guess will create recognizable correlation peaks, a strong statistical match between their hypothetical key and the observed physical reality.
And this is how they get AES 256's complexity down from 2 to the power of 256 to that incredibly vulnerable 2 to the power of 13. Think about that. It's like going from needing to search every single grain of sand on every beach in the world to just a handful of buckets. That's how dramatically these attacks reduce the effort. It truly underscores why you, our listener, should care. AES 256 isn't just some obscure algorithm. It's foundational to virtually all our digital security, from secure websites to your encrypted messages. Imagine the implications if a smart lock or even your encrypted messages could be cracked with such relative ease simply by listening to its power hum. It truly makes you question everything.
And to effectively assess this vulnerability, researchers use a standardized methodology known as Test Vector Leakage Assessment, or TVLA. TVLA is a model-independent way to detect leakage, meaning it doesn't require the attacker to have a specific statistical model of the chip's internal operations. It's a fundamental diagnostic tool in this field.
So it's more like a general sniff test to see if there's a leak, rather than needing to pinpoint the exact key byte. It's about confirming the existence of a vulnerability.
Exactly. The core of TVLA involves applying Welch's 2 test. This statistical test compares the power or EM traces collected when the cryptographic device processes fixed plaintext inputs against traces collected when it processes random plaintext inputs. If there's a statistically significant difference between these two sets of traces, it indicates that the device is leaking information related to the secret key, even if you don't know exactly what that information is. It flags the vulnerability.
And there's a specific threshold for this, a universally accepted benchmark, correct?
Yes, a crucial metric in the hardware security community. A T-score exceeding 4.5 is considered to indicate meaningful leakage. This threshold is widely accepted as a clear sign that the device is vulnerable to side-channel attacks. We'll be referring back to this threshold as we discuss the effectiveness of different countermeasures serving as our scientific barometer for security.
So now that we truly grasped the invisible threat, let's turn our attention to the evolving shield. This is anything but a static battle. It's a relentless, high-stakes arms race, a true cat-and-mouse game where every attack innovation demands a new defense, and, well, vice versa.
This truly is a strategic contest, a perpetual push and pull for dominance. Every advancement in attack methodology spurs new defensive techniques, and in turn, those defenses become targets for even more sophisticated attacks. Historically, the security community has responded to SCAs with various countermeasures, broadly categorized into architectural, logic level, and physical circuit level approaches. Each represents a different battleground in the silicon.
Let's start with the early countermeasures, these broad categories. What exactly are architectural countermeasures, and how do they try to thwart these attacks?
Okay, architectural countermeasures involve modifying the cryptographic algorithm itself, or how it's executed, to make the side channel leakage less predictable. Examples include algorithmic shuffling, where the order of operations is randomized to obscure the data-dependent patterns, or multiplicative masking, which introduces random values into intermediate computations, attempting to hide the sensitive data within a cloud of noise. The core idea is to disrupt the direct correlation between power consumption and the sensitive data being processed.
That sounds like a smart approach, trying to scramble the signal from within. Why isn't that a complete solution that we just use everywhere?
Well, while they introduce complexity and obfuscation, these methods often come with significant limitations. They can be incredibly complex to implement correctly without inadvertently introducing new vulnerabilities. Algorithmic shuffling, for instance, has limited capability against more advanced attacks because only a finite number of operations can actually be randomized effectively. The time-domain signal-to-noise ratio, or SNR, that's the strength of the leaked signal compared to background noise, can still remain too high for determined attackers to exploit. And sometimes their efficacy is questioned under specific, more aggressive attack circumstances. They might make an attack harder, requiring more traces, but they rarely make it impossible without significant overhead.
Then we move to logic-level countermeasures, which sounds like a deeper, more fundamental change to the chip itself. What are those techniques trying to achieve?
Logic-level countermeasures involve changes to the very basic building blocks of a chip, the logic gates. Techniques like WDDL, which is wave dynamic differential logic, SABL, sense amplifier-based logic, dual-rail precharge logic, or Boolean masking, they aim to make the power consumption more constant, regardless of the data being processed. Instead of scrambling the signal, they try to equalize the power drawn across different operations, so a 0-bit consumes the same power as a 1-bit, for instance.
These sound like a more direct, elegant attack on the leakage problem at the fundamental gate level. Why couldn't we just use these everywhere, especially for devices where security is paramount?
They are indeed more direct, and many of these solutions are synthesizable, meaning they can be automatically designed and scaled using standard electronic design automation tools, which is a big advantage. However, they typically come with a significant drawback: high power and area overheads. We're talking about doubling or more the power consumption and chip area. Imagine your smartphone battery dying twice as fast, or a smart home device being physically twice as large because its security circuit needed so much space. That's simply not feasible for resource-constrained devices like many IoT gadgets, where every milliwatt and every square millimeter of silicon counts. These trade-offs limit their universal adoption.
So the quest for robust, practical security continued, leading to the rise of physical or circuit-level countermeasures. This is where the innovations shifted focus, trying to tackle the problem without the heavy penalties of earlier methods.
Exactly. These solutions aim for lower overhead while still providing robust protection, making them practical for the compact, power-sensitive embedded devices that dominate our modern world.
They focus on manipulating the actual physical signals to obscure the information, often by directly affecting the current flow or EM emissions. We've seen a clear progression of these techniques over the years, each trying to push the boundaries of security and efficiency.
Give us some examples of what came before our stellar in this physical circuit level category. What were the pioneers trying and what were their limitations?
Certainly. One notable early example is the switch capacitor current equalizer, or SCCE. This approach achieved a respectable 10 million minimum traces to disclosure, MTD. That's the number of traces an attacker needs to collect to reveal the secret key. However, it came with a significant performance overhead, a doubling of performance degradation due to large capacitor droop, where voltage levels would sag temporarily. Another category involves voltage regulator-based solutions, like the integrated buck regulator, IBR, and randomized digital LDO, RDLDO. These provided medium security, typically less than 10 million MTD, by introducing randomization into their voltage regulation. However, IBR, for instance, involved large passive components that could themselves radiate electromagnetic information, inadvertently creating new potential leakages. Digital LDOs, by their very nature, inherently leak information as their voltage compensation tracks the instantaneous current drawn by the crypto engine.
And then came Stellar. That was heralded as a pretty big leap in this evolution, wasn't it?
Stellar, short for signature attenuation embedded crypto with low-level metal routing, was indeed a significant leap forward. It was the first method to achieve over 1 billion MTD against side-channel attacks by employing an analog cast-coded current source. This analog component provided extremely high signature attenuation, essentially. It acted as a highly effective muffler for the data-dependent physical signals, making them incredibly difficult to distinguish.
So, a billion traces to crack it sounds fantastic. What was the problem if it offered such incredible security? Why couldn't we just mass produce Stellar?
The challenge was that Stellar, relying on a complex, finely tuned analog design, was not synthesis-friendly. This means it's incredibly difficult and time-consuming to adapt and scale to new chip manufacturing technologies. Each new technology node, as chips constantly shrink and evolve, would require significant manual engineering effort and redesign, which is simply not practical for mass production. To address this, Stellar was developed, attempting to make Stellar synthesizable. It managed to achieve an even higher MTD of over 1.25 billion by cascading digital attenuation with other techniques like a time-varying transfer function.
But there was still a challenge, even with Stellar's attempt at making it synthesizable. It sounds like they almost got there.
Yes. The digital attenuation part of Stellar alone wasn't as strong as the original analog cascoded structure. It replicated a source-degenerated structure, which has a lower inherent output impedance and thus lower attenuation. So to reach similar security levels, it required additional complexity and overhead by combining it with multiple techniques. It moved away from a single generic solution, making it less elegant and potentially more difficult to integrate universally.
So, if I'm understanding correctly, the core problem, the big question, has been, how do you achieve truly high signature attenuation, that incredible ability to hide the physical signature of data processing in a way that is both highly effective and easily synthesizable for modern digital chip design? That's the critical engineering challenge, the strategic gap that our Stellar steps up to solve. It's the next evolution in this relentless security arms race. And that brings us to the star of our deep dive, our Stellar. This groundbreaking work takes the incredible benefits of that powerful, high-attenuation, analog cast-coded current source we just discussed, the one that made Stellar so effective but so hard to manufacture, and ingeniously brings it directly into the digital domain. Our Stellar is like taking that secret sauce and finally making it work in a modern, scalable kitchen ready for mass production. Here's where it gets really interesting.
Indeed. The primary goal of our Stellar is to deliver exceptionally high signature attenuation, resulting in a significantly elevated minimum traces to disclosure, specifically over 200 million MTD against SCAs. All of this while ensuring the solution is synthesis-friendly, meaning it can be automatically designed and scaled across different technology nodes, which is absolutely crucial for wide adoption in the industry today.
At the heart of our Stellar is something called the Digital Cast-Coded Current Source, or DCCS. Before we dive into its mechanics, let's just quickly reemphasize what exactly is signature attenuation in this context, and why is it so vital for hiding these physical leaks?
Right. Signature attenuation can be thought of as a kind of active noise-canceling circuit, but for the chip's power and electromagnetic signatures. When the crypto engine is operating, it inherently generates these tiny, data-dependent fluctuations in current and EM emissions. Signature attenuation works by actively flattening these fluctuations, making the observed physical signature constant regardless of the data being processed. This effectively hides the sensitive information. The key physical parameter for achieving high attenuation is having a high output impedance in the current source that supplies the crypto engine. Think of high output impedance like a very thick, unyielding buffer or a dam. It isolates the crypto engine's fluctuating current demands for the main power supply line, so that the power supply's observed current remains flat and unrevealing, no matter what internal data dance is happening.
So the goal is to make the power supply look completely smooth and unwavering from the outside, even if there's a lot of activity internally. And how does our Stellar's DCCS manage to replicate this high output impedance, this analog-like performance, purely in the digital domain? That sounds like quite the engineering feat.
It's not magic, but it is incredibly ingenious circuit design, a fundamental breakthrough. The DCCCS uses two KMOS transistors. These are types of field effect transistors, essentially digitally controlled switches, common in modern digital circuits, configured in what's known as a cascoded arrangement. This stacking of transistors helps achieve high output impedance. The real innovation lies in how they manage the biasing of these transistors, setting their operating points. The lower PMOS transistor is biased by a simple, self-connected NOT gate, which intrinsically generates a voltage around half of the supply voltage, VDD2. This is a clever and stable way to get an intermediate voltage.
Okay, so that sets one transistor, but what about the upper PMOS? That typically requires a more precise, flexible bias, right?
For the upper PMOS, this is where the genius truly unfolds. They use a stack of NAND gates, specifically 3 stages, each with 16 self-connected NAND gates. By connecting one input of a NAND gate to its output, it functions as a self-biased inverter, essentially acting as a fixed digital resistor. But here's the clever part. By controlling the other input of these NAND gates by digitally switching some of them on with a 1, they effectively create a turnable resistive divider structure. It's like having a bank of tiny digital switches that you can flip to precisely adjust the voltage. This allows them to generate a variable bias voltage for the upper PMOS using purely digital components, mimicking what traditionally requires much bulkier and less flexible analog components. For instance, in their 16-stage setup with a 1.2V supply, they could generate voltages ranging from 110 mD to 1.15V. For the SEA experiments in this work, they specifically used a precisely tuned bias voltage of 0.72V.
So they're using basic digital logic gates in a highly unconventional way to create a precisely tunable analog-like voltage. That's quite the engineering sleight of hand. It almost sounds like a magic trick when you describe it. What does that fundamentally change about how we can now design secure chips? Is this the missing piece that finally makes ubiquitous, robust hardware security a reality?
This is a fundamental circuit design breakthrough, precisely because it allows digital designers to achieve what was previously the domain of complex analog engineering. By cleverly using these standard digital components, they've replicated the high output impedance characteristics of much more complex analog cascoded circuits in a completely synthesizable way. This makes high attenuation security much easier to integrate into standard digital design flows, significantly reducing design time and cost. The result is truly impressive. This DCCS achieves an astounding 343 times attenuation. To put that in perspective, Cavia's digital methods, like the DSE in Stellar, only achieved around 30 times attenuation. This is an order of magnitude improvement in hiding those critical physical signatures, making it a critical step towards ubiquitous, robust hardware security.
That's a huge leap in raw attenuation, but the DCCS isn't the whole story, is it? Our Stellar is described as a complete system architecture, implying more layers of defense.
That's absolutely correct. While the DCCS is the core attenuator, the full R-Stellar system architecture integrates 2 critical feedback loops for comprehensive protection against various types of fluctuations. First, we have ring oscillators, or ROs, acting as a local negative feedback mechanism. These ROs form a bleed path of parallel oscillators that effectively bypass any tiny, instantaneous delta changes in the supply current. This system rapidly stabilizes the internal voltage node of the AES crypto engine, known as VAES, and specifically hides the very small key-dependent current changes that are the precise target of side-channel attacks. It acts as a localized rapid response system to smooth out those critical high-frequency fluctuations.
So the ROs are handling the immediate granular fluctuations, the rapid breathing of the chip. What about larger, slower changes, perhaps from different operating conditions?
That's where the switch mode controller, or SMC, comes in as the global feedback loop. This is a slower, overarching control system operating at a coarser grain than the ROs. Its role is to compensate for wider fluctuations that occur due to factors like process variations during manufacturing, changes in the overall supply voltage, VDD, or variations in temperature, collectively known as PVT, for process voltage and temperature. It also handles sudden significant changes in the cryptocurrent if the encryption engine's operating frequency shifts. The SMC ensures the overall stability and proper operation of the AES engine under a wide range of varying environmental and operational conditions, providing a broad adaptive control layer.
So, by combining the DCCS for its incredible signature attenuation with these two sophisticated feedback loops, the fast local ROs and the slower global SMC R-Stellar provides a truly robust, synthesizable, and scalable solution for hardware security. It's a multi-layered defense designed from the ground up to be resilient, addressing both the micro and macro challenges of power delivery. Okay, so you've got this amazing new shield, R-Stellar. It's digitally sound, offers incredible protection, far outperforming previous digital solutions. It seems almost unassailable. But in this never-ending security race, the attackers don't just stop at the first wall. The moment one defense rises, attackers begin searching for its Achilles heel. What if they figured out a way to break your shield itself? That's the terrifying next frontier, isn't it?
That is precisely the crucial question this research tackles, and it represents a significant step forward in understanding the full security landscape. Historically, this has always been the case in cryptography. New defenses inevitably lead to new attack vectors, and a truly robust system must anticipate this. For the first time, this work not only developed R-Stellar, but also explored an attack specifically targeting a physical side-channel countermeasure. It's a testament to the ongoing strategic contest, highlighting that even when you build a stronger wall, the adversary will try to find a way to make that wall work against itself.
And this novel attack is called the Voltage Drop Linear Region Biasing, or VLB attack. It sounds complex, but let's break down its modality. How does an attacker actually launch this kind of attack against a sophisticated countermeasure like R-Stellar?
The VLB attack is incredibly clever because it exploits the very mechanisms R-Stellar uses for stability. It specifically manipulates the switched mode controller, or SMC, loop, that global negative feedback we just discussed, that stabilizes the circuit under varying conditions. Let's set up the scenario. Normally, our crypto engine draws a certain amount of current, say 15 units of current, which is supplied by a specific number of current source, or CS, slices operating in their saturation region. This is their ideal operating mode, where they provide high attenuation and protect against side-channel leaks.
So the system is secure under these normal operating conditions, with the current sources doing their job, acting as that high-impedance buffer.
Correct. Now, the attack begins. An adversary, through trial and error, deliberately and slightly reduces the overall supply voltage, VDD. This isn't a massive drop that crashes the system, but a subtle reduction. This abrupt voltage drop might initially cause the encryption engine to falter or draw insufficient current. But here's where the SMC global negative feedback loop, designed for stability, kicks in.
And how does the SMC, this global stabilizer, respond to this intentionally reduced supply voltage? It's trying to keep things running, isn't it?
Exactly. To compensate for the reduced supply voltage and maintain the required current for the crypto engine, because the crypto engine still needs its 15 units of current to operate the SMC loop, dynamically activates additional CS slices. For example, if each CS slice can now only provide, say, 3/4 of its normal current due to the lower VDD, the SMC will activate more slices, perhaps 20 slices, instead of the original 15 to collectively deliver the needed 15 units of current to the encryption engine. It's working harder to maintain the output.
This sounds like the system is doing exactly what it's designed to do. Adapt and try to keep the crypto engine running despite a difficult external condition. So what's the critical flaw here? Where does the compromise actually happen if the system is seemingly compensating?
This is the absolute key insight of the VLB attack. These additional activated CS slices, necessary to maintain current under the reduced VDD, are now operating in the linear region, not their intended saturation region. To use our faucet analogy, in saturation, the faucet is tightly controlled, giving a constant flow, current, regardless of small changes in water pressure, data processing. In the linear region, however, it's far less controlled, and its flow will fluctuate much more noticeably with any subtle pressure changes. This translates to a drastically reduced output impedance of these current sources. And if you remember from our earlier discussion, high output impedance is what gives us that high signature attenuation, that effective buffering.
Ah, so it's like a shield that suddenly becomes transparent, or a noise-canceling headphone that stops working. The attenuation, R-Stellar's primary ability to mask the physical signatures, is severely compromised because those current sources are pushed into a less efficient, more leaky operating state.
Precisely. The attenuation is significantly reduced, leading directly to heightened information leakage. It's a subtle but devastating shift in how the countermeasure functions, turning a robust defense into a vulnerable one. It's important to note, though, that this attack is only feasible under specific circuit conditions, as defined by Equation 2 in the research paper, where the current sources in their linear region can still drive the crypto core without the system completely crashing, allowing the leakage to occur.
So what's the real-world impact of this VLB attack? How dramatically does it weaken our Stellar's defenses, bringing that seemingly unassailable protection back down to a dangerous level?
The impact is quite severe. Under a VLB attack, our Stellar's impressive minimum traces to disclosure, which was over 200 million traces in normal operation, plummets dramatically to just 105,000 traces. That's a reduction of over 2,000 times in the number of samples an attacker needs.
That's a massive shift. It turns a practically unassailable defense, needing potentially hundreds of millions of samples, into something that could be broken relatively quickly, which highlights why this novel attack is so significant. And what about TVLA, our leakage meter? Does it confirm this compromise?
Absolutely. With TVLA, meaningful leakage that T-score exceeding 4.5 is detected from as few as 3,000 traces under a VLB attack. This confirms that the information is leaking very rapidly and measurably. This novel attack truly demonstrates that even the most advanced physical countermeasures can be targeted and compromised if they lack awareness of such attack vectors.
Yeah.
The cat-and-mouse game, as we said, is truly relentless.
Oh, 105,000 traces. That's a massive shift. It turns a practically unassailable defense into something that could be broken relatively quickly. So if attackers are always thinking one step ahead, trying to find the next weak link, then an advanced defense like our Stellar can't just be strong. It also needs intelligence, doesn't it? It needs to know when it's being targeted. How did the researchers address this next critical layer of the battle building, a countermeasure?
Exactly. Given the discovery of such a sophisticated attack, the practical adoption of physical countermeasures in industry, especially for critical infrastructure and embedded systems, hinges on their ability to detect and mitigate these new attack vectors. This is precisely where the intelligent attack detector becomes absolutely crucial for maintaining trust and applicability. It transforms a reactive defense into a proactive, self-aware one.
So how does this VLB attack detector actually work? Does it require a whole new set of sensors and circuits, adding significant overhead, or does it cleverly reuse existing components? That would be a far more elegant solution.
That's one of the most elegant aspects of this design. It cleverly leverages existing components, minimizing overhead. The system smartly reuses the ring oscillators, or ROs, that are already present to stabilize the VAES node, that's the crypto engine's internal voltage. It repurposes internal diagnostic tools as attack sensors.
So the same ROs that are part of the local negative feedback, smoothing out those tiny current fluctuations, are now doing double duty as an attack sensor. That's brilliant design economy.
Precisely. They are the foundation of the detector. The system employs a dual RO measurement approach. One RO is dedicated to estimating the VAES voltage, the voltage at the crypto engine's internal node. A second, replica RO, is then ingeniously used to estimate the global VDD, which is the main supply voltage. To make the voltages comparable for accurate measurement, this global VDD is passed through a stack of inverters, effectively dividing the voltage to approximately 2/3 of the VDD. This ensures that, under normal conditions, the two voltage estimations, VAES and the scaled VDD, should be very close to each other.
Okay, so you're essentially measuring two very similar voltages, the internal crypto engine voltage and a carefully scaled version of the main supply voltage. How do those subtle voltage measurements then translate into definitively detecting an attack?
Both RO outputs, which are essentially frequencies that vary with the voltage they're measuring, are then frequency divided and fed into asynchronous counters. This process reliably converts the analog voltage information into distinct digital counts. These two counted values, representing VAS and the scaled VDD, then go into a digital comparator.
And the logic here is that if an attacker deliberately drops the VDD, that subtle reduction will cause the two counted values, which should be nearly identical, to diverge, right?
That's precisely the logic. Ideally, under normal operation, the two counted numbers should be very close, within a tight tolerance. However, if VDD is intentionally reduced by an attacker, the difference between the two counter outputs will surpass a predefined configurable threshold. When that difference crosses the threshold, it immediately signals that a malicious voltage drop attack, specifically a VLB attack, is underway. It's like a finely tuned alarm going off.
And what happens once the attack is detected? Does the system just notify someone, or does it take immediate, decisive action to protect the secrets?
It takes immediate, decisive action. Upon detection, the system activates protective measures, most notably halting the encryption engine. This is a critical, proactive response because it prevents any further leakage of sensitive information, effectively shutting down the attack vector before any meaningful data can be extracted.
And the speed of this detection is absolutely astonishing. You mentioned it detects the VLB attack within a mere zero point 0.8 milliseconds, less than a millisecond. To put that in perspective, if AES-256 is running at 20 millihertz with 14 rounds, only about 1.1% of one single encryption is even possible in that tiny window before the system shouts stop. This essentially makes any practical SCA attack impossible within that time frame because the attacker simply cannot collect the tens or hundreds of thousands of traces needed before the system shuts down.
The speed is absolutely paramount here. The VLB attack, as we discussed, requires about 105,000 traces to retrieve the key. With a detection time of 0.8 milliseconds, an attacker simply cannot collect anywhere near enough leakage window to extract those traces before the system proactively shuts down. This renders the VLB attack practically useless against our Stellar with its intelligent detector enabled, effectively closing the window for any meaningful data exfiltration.
The significance here is truly immense. This isn't just about building a stronger shield. It's about building an intelligent shield that actively knows when it's being attacked and can defend itself. This self-awareness elevates hardware security to a new level.
Absolutely.
Yeah.
This is the first time that an attack on a physical side-channel countermeasure has been explored in such detail, and a corresponding self-aware attack detector has been experimentally validated in silicon. This adds a crucial layer of trust and applicability to these advanced physical countermeasures, which is essential for their widespread adoption in embedded systems, critical infrastructure, and consumer electronics. It represents a new paradigm in hardware security, with the ability of a defense to detect when it itself is under assault becomes as important as the strength of the defenses themselves.
All this sounds incredibly impressive in theory, but the proof is always in the pudding, or, in this case, in the silicon. These researchers didn't just design this, they built it, they fabricated it, they tested it rigorously, and they threw everything they had at it to prove it works in the real world. Let's dive into the concrete, real-world validation and measurement results.
Absolutely. The researchers fabricated an actual integrated circuit, or IC, a 1 millimeter square chip, using the TSMC 65 nanometer CMOS low-power process that's a widely adopted and modern manufacturing technology for MIDI chips you interact with daily. This IC features a fully functional AES-256 crypto engine as the target for protection, alongside their R-Stellar countermeasure.
And how big is the R-Stellar countermeasure itself on the ship? Is it a massive addition that negates its practicality?
It's not at all. The R-Stellar countermeasure occupies a compact 0.048 square millimeters of active area. To give you some context, the AES-256 core itself takes up 0.14 square millimeters, so the protection mechanism is relatively small, less than half the size of the engine it's protecting, which is a strong indicator of its efficiency and practicality for integration into existing designs.
They also had a pretty sophisticated testing rig to put this to the test, simulating real-world attack scenarios, right? This isn't just lab bench measurements.
They absolutely did. For precise measurement, they used a high-speed 5 gigasamples per second oscilloscope to capture detailed power traces, along with an H-probe with a 10 millimeter diameter for collecting electromagnetic, or EM, traces. The faint EM signals were then amplified by a wide-band amplifier. A National Instruments DAQ card was used for configuring the chip settings, and an arbitrary waveform generator, or AWG, supplied the necessary clock and control signals for the AES engine. And crucially, they used a controlled power supply that could be precisely manipulated by a computer to simulate the voltage drop linear region biasing, or VLB attack we discussed. This allowed for rigorous, repeatable, and real-world testing of both R-Stellar's defenses and its detector.
So let's get to the numbers, the hard evidence. How did R-Stellar stack up against an unprotected AES-256? What did the security evaluation reveal about its baseline effectiveness?
Well, the time domain traces provide incredibly compelling visual evidence of the attenuation. When you look at an unprotected AES-256, you see clear, prominent data-dependent fluctuations in the power and EM signatures, like a clear heartbeat revealing internal state. With R-Stellar enabled, those signatures are visibly flattened and smoothed out significantly. The difference is stark, immediately illustrating the concept of signature attenuation.
And for an unprotected AES-256, what were the vulnerabilities in concrete numbers? How quickly could an attacker succeed?
For an unprotected AES-256 implementation, a standard correlational power attack, or CPA, could reveal the secret key in just 2,300 traces. For a correlational EM attack, CIMA, it took only 4,400 traces. And using TVLA, our general leakage detection method, meaningful leakage was detected within a mere 100 traces. These are incredibly low numbers, highlighting just how vulnerable unprotected systems truly are to even basic side-channel attacks. Keys could be compromised in milliseconds.
That's terrifyingly fast. What about our stellar protected AES-256 under normal operation? Before any intelligent VLB attack on the countermeasure itself, did it live up to its promise of high attenuation?
Here's where our stellar truly shines, demonstrating its formidable baseline defense. Under normal operation, with our stellar protecting the AES-256, the secret key was not revealed even after analyzing 200 million traces for both CPA and CIMA. They looked across a wide frequency spectrum from 100 MHz to 2 GHz and found no peak correlation, indicating absolutely no discernible leakage. With TVLA, meaningful leakage only appeared after a staggering 2.5 million traces for EM and 5 million traces for power.
Wow. This translates to an improvement of 250,000 times to 500,000 times compared to an unprotected implementation. That is a truly monumental leap in security for a single synthesizable countermeasure. It's like going from a lock that can be picked in seconds to one that would take centuries, given typical attack speeds. This isn't just an incremental improvement, it's a paradigm shift in how resilient a single hardware countermeasure can be.
Exactly. It sets a new benchmark for what a single, generic hardware countermeasure can achieve in terms of raw resilience against these types of physical attacks, making it a highly attractive solution for modern embedded systems.
But what happens when that intelligent VLB attack we discussed is launched against our stellar? We've seen how effective our stellar is normally, but how does it fare when its own defenses are under an intelligent, targeted attack designed to bypass its primary attenuation?
Under a malicious VLB attack, the measurements confirm the compromise we predicted. We saw a visibly increased power trace amplitude compared to normal R-stellar operation, which unequivocally indicates that the attenuation was indeed reduced and information was leaking again. When a CPA was performed under these specific attack conditions, the correct key was retrieved to just 105,000 traces. That's a dramatic reduction from the 200 million traces required under normal R-stellar operation, confirming the attack's effectiveness.
And that TVLA score. How quickly was meaningful leakage detected when the VLB attack was active?
Under the VLB attack, meaningful leakage was detected from as few as 3,000 traces using TVLA, confirming the severe compromise and the rapid reestablishment of a leakage channel. This was further validated through frequency domain CPA at 400 MHz. The measurements definitively proved that the VLB attack successfully bypassed R-stellar's primary attenuation mechanism if left undetected.
So, the VLB attack is clearly effective at compromising R-stellar's primary defenses. Now, for the ultimate test, what about the attack detector's performance? Can it actually catch this stealthy attack in time before any meaningful information can be leaked?
This is the critical piece that brings the security full circle, demonstrating the system's holistic intelligence. The attack detector successfully detects the VLB attack within a blazing fast 0.8 milliseconds, and it does so with 100% accuracy in every test run.
Less than a millisecond. To put that in perspective again, if AES-256 is running at 20 megaliter with 14 rounds, only about 1.1% of one single encryption is even possible in that tiny window before the system shouts, "Stop." This essentially makes any practical SCA attack impossible within that time frame because the attacker simply cannot collect the tens or hundreds of thousands of traces needed before the system shuts down. The window for leakage is effectively slammed shut. This rapid and accurate detection completely neutralizes the VLB attack's ability to extract keys. Even though the attack can technically compromise the attenuation, the detector ensures that an attacker has no practical window to collect the necessary data, proving that the detector is not just a theoretical concept, but a robust, experimentally validated solution that restores the system's unassailable security.
And when you compare our stellar to other state-of-the-art countermeasures, especially given all these layers of defense, it really stands out, doesn't it?
It absolutely does. While other advanced techniques might achieve high MTD by combining multiple, often complex strategies, our stellar achieves over 200 billion MTD as a single, generic, and crucially synthesizable countermeasure. But its truly unique capability, the one that sets a new industry benchmark, is its built-in, experimentally validated ability to detect attacks on the countermeasure itself. That self-awareness, that ability to defend its own defenses, is a game changer for the trust and applicability of physical security solutions in our increasingly connected world. #tag outro.
What an incredible journey we've been on today. We started by imagining our most secure digital data being vulnerable not to complex code breaking, but to the subtle hum of a chip or the faint flicker of its power usage. We've journeyed from understanding these insidious side channel attacks that can reduce the effective complexity of AES 256, from virtually infinite to a mere 2 to the power of 13, to exploring R Stellar, a cutting edge defense.
We've seen how RScaler achieves incredible resilience, over 200 million traces to disclosure, by cleverly bringing analog-like signature attenuation into the digital world. But perhaps even more remarkably, we've explored its intelligent ability to recognize and shut down a novel attack, the VLB attack, specifically designed to bypass its own defenses by pushing its current sources into a vulnerable linear region.
And the speed of that detection is just breathtaking. Zero point 0.8 milliseconds. That's faster than any attacker could hope to collect enough information to compromise the system, effectively neutralizing the threat and proving that hardware can indeed defend itself from sophisticated physical attacks. It's a true testament to human ingenuity in this relentless security arms race.
This work truly represents a significant step in the ongoing cat-and-mouse game of hardware security. By not only building strong, scalable defenses, but also integrating self-awareness against attacks on those very defenses, our Stellar establishes a new benchmark for resilient cryptographic systems, particularly in the critical realm of physical countermeasures that underpins so much of our digital trust.
Yeah, the broader implications of this kind of innovation are immense. This isn't just about an academic paper. This technology is crucial for protecting the vast array of embedded systems and IoT devices that power our modern world. From the security chip in your smartphone, to the controls in autonomous vehicles, to the hidden infrastructure of smart cities, these are the foundational layers where sophisticated physical-level threats need to be constantly battled.
For you, the listener, this means a deeper understanding of the intricate, often unseen, battle being fought to keep your data safe, far beyond just passwords and software updates. It's a powerful reminder that security is a multi-layered challenge, extending all the way down to the physics of the silicon itself.
Indeed, the digital world is constantly evolving, and with it, the methods of attack and defense. While our Stellar offers a formidable shield and a watchful eye against known physical vulnerabilities, it makes you wonder what new, unforeseen physical attack vectors might emerge in the future as attackers continue to innovate. And how will the next generation of resilient systems learn to protect against those? The dance between attacker and defender, it seems, will never truly end. Thanks for joining us on this deep dive into the digital frontier.